welcome everybody to the webinar number 39 of the IEEE Ag Robotics and Automation Technical Committee, July 2016. And today we are happy to have with us Gökhan Bayar from, and Gökhan, please tell me if I'm pronouncing this correctly, Bülent Ecevit University in Turkey.
Yes, it's correct.
Okay, very good. And Gökhan is going to present the work that he did during his PhD, which is about improving the trajectory tracking performance of autonomous orchard vehicles by including the compensation of wheel slip in the dynamic model formulation and then in the control methods. This is work that Gökhan, I'll leave the abstract here for everybody to read. This is work that Gökhan did partly at Carnegie Mellon in our group at the Field Robotics Center. So it's great to have Gökhan back, so to speak, and to present the results of the work that he did when he was at Carnegie Mellon. And when was that, Gökhan? 2013 or 2014?
Yes, 2 years ago. No,
2 years ago. So,
no, 3 years ago.
3 years ago, 2013, when Gökhan spent a year with our group at the Field Robotics Center, helping us develop dynamics and control methods for autonomous orchard vehicles. So again, it's great to have Gökhan back, especially at this time of the year when not only Gökhan just had a baby a few weeks ago, so he's not extremely busy, but his country, of course, is going through some turmoil, and everybody's certainly following the events there. And still Gökhan is very generously coming to the group and presenting despite the situation, his personal situation and his country situation. So Gökhan, we are happy to have you. Gökhan, like I said, he spent a year with our group at the Field Robotics Center as part of his PhD that he got in mechanical engineering from the Middle Eastern Technical University in Turkey, where he also got his master's. Gökhan's specialties are in dynamics and controls and system development in general, and especially ground robots. He has a long history of developing ground robots for commercial and military projects in Turkey and with our team at Carnegie Mellon. And he now leads the robotics group at Bülent Ecevit University in Turkey, which I understand is in a city on the coast of the Black Sea, a beautiful port city, and a place I'd love to visit sometime with Gökhan. So with that, let me ask everybody once more, please click on the little person icon on the Join Me app. And if you see viewer as opposed to your name, you should see your name. If you don't see your name, click on the topmost viewer and then change that to your name. And also, please mute your microphone or your phone at this moment. And now, Gökhan, we are going to, as we do every month, trust the miracles of technology and pass the presentation rights to you.
Okay.
So the Join Me app should be telling you now to accept the presentation role.
Sorry.
Are you joining using the Join Me app or the website?
No, I did not get such a question actually.
Okay, do you have the Join Me app running?
Actually, now downloading the desktop application is seen. Actually, I have installed this one.
So if it's going to download, why don't we do it differently and present from here?
Okay, sorry, I am trying to install that one. Actually, I have installed this Join Me application.
Okay, why don't you please run?
Now, can you see my slides?
No, are you running the application?
Yes, yes. Now it's connecting. It says connect.
Okay. And you have to connect to that number 250-644-990.
Okay, it says connecting.
How is your internet connection?
Internet connection is good. It says still connecting.
Okay, for now, let's go with this one. Can you see the slide? Can you see the slide, Gokhan?
No, no.
Can anyone else see the slide that I'm sharing? That's Gokhan's own presentation.
Yeah, I can see.
Okay.
Yes,
So
I
someone see that. All right, Gokhan, why don't you go back to the previous window
Okay.
where you could see my introduction?
Actually, now in the web page, it says, feel free to close this web page. Your meeting is running in the downloaded Join Me program. So should
Okay.
I close the web page?
Let's try that. Let's try to run
Okay.
through the app.
Now the application is saying it is connecting. I am not sure. Is there any restriction? The web.
That's okay. So why don't we do the following? Open the presentation, the exact presentation you sent me,
Okay, I am.
and I'm going to present it here.
Okay, now the presentation is open.
Okay, and you tell me, go to slide 2, go to slide 3, go to slide 4, and I'll do that for you.
Yes, actually I can say yes.
Okay?
Now let me open the Join Me web page again. Yes, now I can see. Okay.
All right. So you tell me, go to next slide, go to next slide.
Okay.
This call is being recorded.
Okay, someone, Gokhan, you need to turn off the microphone on your computer.
Okay, now everything is okay.
You,
Should I start?
yes.
Okay. Actually, I am sorry. I did not understand what is the problem.
Okay. Gokhan, here's what you need to do. I believe, are you calling on the phone or on the... You need to turn off either your phone or the microphone because they are creating echo.
Now it's okay?
Let's try this.
Okay. I am starting. I am really sorry for this case. I did not understand. There is maybe internet restriction, I don't know. And today my talk is about improving autonomous orchard vehicle trajectory tracking performance via slippage compensation. As Marcel said, this study was conducted under the supervision of him in the Field Robotics Center of Robotic Institute of Carnegie Mellon University. Next slide, please, Marcel. So the objective of this research is to develop a slippage estimation procedure and perform a desired trajectory tracking control. And here we are seeing a small control block. The aim is to get some feedback information to the slippage estimation block. So this block is fitted by position and orientation information of the vehicle and steering angle and forward velocity, and the output is the slippage occurring at front and rear. Next slide, please. So in general, the mobile robots and autonomous vehicle researchers are assuming that a single set of controller and parameters or a unique equation of motion can be used in order for creating a trajectory tracking. However, in real-time applications, this is not true due to changing the characteristics of wheel-ground interaction. So, why we have studied in this research topic. Next slide, please. So, as I said in the previous slide, there are some simple assumptions in mobile robot and autonomous vehicle applications. And for instance, the assumptions are ideal transmission, ideal rolling, no slippage, no cost of traction control, no external wheel forces, no surface change behavior, no disturbance, something like that. In this study, we did not use such assumptions, I have to say that. Next slide, please. So here is the general control system block of our system. So our system has a desired task, and this task goes through the vehicle model, and we have a controller. This controller is creating a forward velocity and steering angle for the autonomous ground vehicle. And in our case, we have investigated the wheel ground interaction and surface information should be inside the vehicle model. Next slide, please. So as a general approach, the trajectory tracking control of an autonomous vehicle can be modeled by using this simple representation. So the vehicle should have a desired trajectory, and in the real-time operations, there is an actual reference path. So the difference between the actual and desired trajectories can be modeled by using simple difference equations. The x error, y error, they are the positional error, and the theta error is the orientation error of the vehicle. Next slide, please. And for generating the desired trajectory in literature, there are some methods are used. For instance, the first method is the dynamic approach. As an example, the bicycle model is commonly used in the autonomous vehicle applications. The kinematic car-like robot approach, it is really popular. Also in our study, we have used this one. Point mass model is also used, so the vehicle is considered as a point, and the Dubin's curves is also used frequently in such applications. Next slide, please. So in our study, we have used car-like robot model, and the equational set is also shown. Why we have chosen this model? If the vehicle's forward velocity is really slow, this model works properly. So slow means, for instance, in our application, the forward velocity was between 0.5 meter per second to 2 meter per second. So in order to use this model, you need only the orientation of the vehicle, forward velocity of it, and the steering angle information. Next slide, please. So in order for constructing a model, motion model and controller, we have used this such simple representation. So in this system, we have a desired path or trajectory and the vehicle in real operation, and always there are some errors between longitudinal lateral directions and also orientational error. So using such simple representation, we can easily set up a model. Next slide, please. So this slide shows the general idea about the of our control system. So we have the desired position and desired orientation for the vehicle. We have a controller. This controller is able to generate the forward velocity and steering angle commands, and also we are using some feedbacks. These feedbacks are the position, velocity, and steering angle of the vehicle, and also we are using positional and orientational errors. For instance, in this slide, we are using the XPC and so RTK GPS, so we are calling this XPC, the high accuracy positioning feedback system. I am going to show you some details in the next slide. Next slide, please. So as a simple operation, so we have used the Lyapunov stability criteria. So using this simple approach, we have formed two Lyapunov functions, and using these functions, at the end, we could be able to obtain the controllers for forward velocity of the vehicle and steering angle. Next slide, please. And in this slide, I want to show the working environment of an orchard robot vehicle. Here there are some trees, and these trees are forming the lines of trees or rows of trees. In this slide, the objective is that the vehicle should be able to follow the desired trajectory, which lies on this center of two consecutive tree lines. As you can see, all the width of the rows of trees are different. For instance, W1, W2, something like that. And the objective is to find these values also and track the reference path. Next slide, please. So here, I want to show you a reference trajectory that we have developed. So here the straight lines are showing the reference trajectory, which lies on the centers of two neighbor rows, and the circles are showing us the turning geometry from one row to another. Next slide, please. So this slide is about the turning geometry. It is one of the problems in real applications. Why? Since generally in some orchards there are always not some available space for turning. So in order to solve this problem, we have developed such a geometry. So using the geometry variables, we can easily set the turning geometry. And in the plot shown in the right, in order to create such a geometry, we have a steering angle profile. The steering angle profile is shown by the dashed lines. However, as you can see, this geometry contains such sharp turning options. So think about in general, the steering mechanisms is a mechanical system. So sharp geometry may harm this mechanical system. So as a solution, we have developed a fourth order polynomial so that the steering angle profile remains smoother. Next slide, please. So I have to say that in our applications, we developed our algorithms in robot operating system ROS under Linux, and we have coded all the operations in C++ environments. Next slide, please. So this is the general picture of the experimental orchards. So the experimental orchards have 8 lines of trees and 7 rows of trees. And this slide shows the real length or width of the rows information. And also the picture has a vehicle, and we have showed this autonomous orchard vehicle in our applications. Next slide, please. And now I want to show you some details. We did so many experiments, and we did these experiments to test the behavior of the proposed model, and also we checked the performance of the model. In the first experiment, we just tested the performance of it, so we did not include the slippage information. In this experiment, we used the RTK GPS in order for getting the position information. Next slide, please. Here is the first example, first result. So this result is about the 4-kilometer autonomous drive conducted in the orchard environment. As you can see, the model did a good jobs, and we did so many real results. Actually, we got nearly 50-kilometer autonomous drive in this orchard. Next slide, please. So in order to complete reference trajectory tracking control, the steering angle profile and output is really important. This slide shows the desired and actual steering angles for the 4-kilometer autonomous drive. As seen, the reference steering angle profile is followed by the controller. Next slide, please. Now I have a video actually, and how can I show you? I don't know. Maybe Marcel can show you. Marcel, if you cannot find the video, we can go to the next slide. And in the second experiment, we test the behavior of the proposed model. And also in this experiment, we did not use the slippage information. Still, we are checking the performance of the control system. And in this experiment, we replaced the RTK GPS with the laser scanner rangefinder. And now we are detecting the trees and also estimating the rows of trees. Next slide, please. Yes, Marcel. Now the video is right top, actually. Right top. No, right top. Yes, this one.
Tell me the number 1, 2, 3, 4, or 5.
Oh, 5. 5. Yes, this video shows the steering wheel actually. Now the controller generates the required commands for the forward velocity and steering angle. In this experiment, the forward velocity was 1 meter per second. And in this experiment, we did not use the laser scanner and we did not use the slippage information. We were checking only the performance and accuracy of the proposed model. Okay, Marcel, we can continue the next slide. And in the second experiment, we replaced the RTK GPS with the laser scanner rangefinder. Next slide, please, Marcel. And this still we are using the same control system block. Only the laser scanner rangefinder is placed in our system. Next slide, please. And in this experiment, we use this autonomous orchard vehicle. The vehicle has a laser scanner rangefinder located at front mid-center of the vehicle. And now the purpose of using the laser scanner is to detect the trees and estimate the rows of trees. Next slide, please. And here the story is seen. So using the laser scanner rangefinder, we can able to detect the trees and location of them also. And the estimation of the rows of trees is done by using the simple first order line equations. And we have adapted these systems in the real vehicle. Next slide, please. And now this slide shows the reference trajectory. We used a different turning geometry. Why? Since we have wanted to see that whether our proposed model can be able to work with different geometries. So as you can see, right top picture, we are using a different turning geometry. However, the procedure is the same. we are using still the fourth order polynomial in order to make the steering angle profile smoother. Next slide, please. And this still we are using the same control block, and we have a controller now. We are calling this model-based controller, and we have a roll detection system. This roll detection block is using the laser scanner data. All the tree detection and row estimation procedure are done in this block. We have still the trajectory generator, and at the end, our objective is to try to follow the reference trajectory with minimum tracking errors. Next slide, please. And I want to show you one of the results, and these results are obtained in the first row of the orchard. The width of the orchard is 4.5 meter nearly, and its length is about 53 meters. And in order to show the performance of our system, proposed system, we did our experiments by using our system and the pure pursuit controller. The mobile robots and autonomous vehicle researchers know that the pure pursuit controller is one of the simplest approach in order for tracking a reference trajectory. So as you can see from this results, our method generates really smooth steering angle profile, and the right plot shows the distance between the vehicle and the center of the row. So in both results, our procedure generates really successful results if I do a comparison between the pure pursuit control. Next slide, please. Actually, in this slide, we have 3 videos. I really worked for in order for creating these videos. However, now I cannot show you. All these videos should be working together. Marcel, maybe you can show these videos. So this actually the 3 and 4 and 6.
So 3,
Yes.
3 this one.
Yes, and next one.
It's a little slow, but it's coming up. So somehow this one did not work. Why don't we go back?
We can watch the other slide. Yes, this one. So actually, let me explain something. In this experiment, I have used 2 cameras. Now I am seating the seat drive, and I am using the camera. At the front of the vehicle, there is another camera, so I can be able to show you the performance of the system. Also, I have created a laser scanner data video. So while the vehicle is in motion, I have logged the RTK GPS data and laser scanner data, and using or watching this video, we can easily see how the laser data is coming and how the detection procedure works. So as you can see, there is a tripod, so both cameras are recording at the same time. Marcel, maybe we can show the laser video also. It's enough, I think. Yes, yes, this one. We can show really, yes, this is the real data. In this case, the vehicle is in motion and the data was logged, and we can see the trees actually. And using this data in real time, we detect trees and estimate the rows of trees. Marcel, we can continue with the next slide. Next slide, please. And in the next experiment, we are still testing the behavior and performance of the proposed system. Now, we are using the slippage information, and also RTK GPS is used for the position feedback. And next slide, please. And here is the control system block, and still we are using the same control system, and now we have a slippage estimation sub block, and this slippage estimation block can be fed by RTK GPS, laser system, or odometer and steering system. Next slide, please. Here is the general idea of the slippage. So we are assuming that slippage is occurring at front and rear of the vehicle in longitudinal and lateral directions, and also there are two slip variables. That means the front slip angle and rear slip angle, and using the methodology we can find out these slip variables. Next slide, please. And we are using the car-like robot model I have set in previous slide. So without slippage information, car-like robot model is seen in the slide. If we adapt the slippage information in our model, the car-like robot model is changed a little bit. In our experiments, as I said before, the longitudinal velocity is really slow, between 0.5 and 2 meters per second. And also we are saying that the steering mechanisms works at the front of the vehicle. So as an assumption, the slippage at front is to be 0. And now we are trying to find out the slippage information occurring at the rear of the vehicle. Next slide, please. Before testing our system in the real orchard, we have tested our system on snow. So here we have some pictures, and the slippage experiments have been done in the Carnegie Mellon University campus. And now I will show you some results. Next slide, please. So in this results, the trajectory tracking control with and without adding the slippage estimation are seen. As you can see, if we did not add the slippage information into the overall model, the trajectory tracking performance is not good. If the slippage estimation is used inside the model, the desired trajectory tracking control is really nice. Next slide, please. So also in the autonomous mode, the steering angle and forward velocity is important. As you can see from the steering angle results, if the estimation procedure is used, the steering angle profile is really calm, and the results show that if the steering angle is not used, the steering angle becomes really crazy, and it is not so good for the mechanics of the steering system. Also, the forward speed is better than the case which the estimation procedure is not used. Next slide, please. And after doing this experiments, we tested our system in an orchard. So slippage information is used, the system model and controller is used. Now we are using the road detection system. Actually, all the system is combined in this experiment. Next slide, please. And as you can see from this picture, the experiment was tested in total mud surface in the experimental orchard. So it was a good opportunity for us to see the performance and accuracy of the system. Next slide, please. And in this studies, we have considered that the vehicle should follow a desired trajectory in order to track the straight reference line, and also in order to track the turning geometry. So the turning geometry is important from one row to another. And why? Since there should be a target box. Okay, inside the picture, you can see there should be a target box, and the vehicle should reach this box. Why? Since after reaching this box, the vehicle can easily go to the next row. And as you can see from this picture, there are some variables SW, SL, SS, SE. These are related to the real orchard parameters. We have generated an algorithm, and this algorithm needs to use these variables, and this system can be used in an orchard case. Next slide, please. And this slide is about the results of the slippage estimation. And we have I have shown you the four results. The results shown by A1 are obtained by using the RTK GPS feedback system. And in this experiment, slippage estimation was not used. And the results shown by A2 are obtained by using the slippage estimation procedure, and also the RTK GPS feedback was used. And the results indicated by A3 are obtained by using the feedback information, and this information is coming through the data reckoning system. However, we did not use the slippage estimation, and the next results shown by E4 are obtained by using the slippage estimation procedure, and in this system, data reckoning feedback and laser scanner and detection system are working. And as you can see, we have a target box, and the objective is to follow the desired trajectory and reach the target box. Next slide, please. And now we have two videos actually, and the first video shows the results. This result is about turning control, and it is not using slippage estimation. And we have to see two videos. Yes, this one. Yes, Marcel. Actually, the other video is showing the ground truth information. If we are able to watch these two videos, we can see easily the turning geometry and the performance of the controller and system model. Marcel, can we see the other ground truth video? Yes, no. The bottom. Yes, this one. Yes, this one. So this is the ground truth video. While the vehicle was in motion, I have logged the RTK GPS data in order to create this video. So the objective is to follow the desired trajectory and to reach the target box. If the vehicle reached the target box, it can easily enter the next row. So the red line shows the longitudinal direction of the vehicle. As you can see, if we don't use the slippage estimation procedure, the vehicle cannot track the reference geometry. Also, it cannot be able to reach the target box. So in order to enter the next row, the vehicle should do some harsh action. Marcel, we can see the other video. Yes, this one. This video again shows the ground truth information, the RTK GPS data, and in this case, we are using the slippage estimation procedure. Marcel video. So as you can see, after adding the slippage information, the geometry.
Thanks, happen here.
So the geometries, trajectories followed, and the vehicle follows or reach the target box. And next slide, please, Marcel. Next slide. Actually, we are done now. And we have published all the details and results, the study of improving the trajectory tracking performance of autonomous orchard vehicles using wheel slip compensation in the Biosystems Engineering Journal. Actually, I would like to send my special thanks to co-authors of this paper. And my presentation now is over. Thank you for attention. I am so sorry for this case. I don't know. Actually, I have tried to prepare some nice videos, nice presentation. However, I don't know. There should be a restriction in the web. I am really so sorry. Thanks for your
Don't worry,
attention.
those things happen every now and then. Thank you very much for the presentation and for the detailed results.
If you have questions.
Yes, let me ask if our audience has any questions for you. People can use the chat window on Join Me, or you can just ask your question on the phone.
Actually, I can get any question.
Let me ask you, how has the work evolved after you went back to Turkey? What other improvements have you guys been able to make, and what vehicles are you applying this work to?
Yes, actually in Turkey, I have designed a small autonomous orchard vehicle. It is still using 4 wheels, and it is a differential one. And the difference is I am trying to design another LiDAR system. You know, the LiDAR system is not so is really expensive, and we have designed really low-cost LiDAR system, and we got really good results. And now we are carrying the system to a steerable vehicle. Actually, now we are working on another vehicle which has 4 wheels, and it has a driving unit at its rear, and it has a steering system at its front.
What types of orchards or crops are you planning on applying the vehicle? What are the main crops in Turkey you can apply this work to?
Actually, here we have lots of cherry orchards, and in Turkey, one of the most important cherries in the world are actually produced. Now we are trying to use these vehicles in this cherry orchards. We got some good results, and we are still working on the system, on the algorithm, and on the vehicle.
Okay, very good. Other questions from the audience?
Just will you show the slides and media? Yes, actually, I can share the slide and media, and I can put all these videos in YouTube or in under Dropbox, and I can share with you. Actually, if you go to this paper has some supplementary materials, and also you can see some videos, different videos.
Very good. Any other questions? Well, Gökhan, thank you very much for the presentation. Again, we understand it's a busy time for you with the new child and the events in Turkey not being favorable to presentations like this. So we appreciate your being with us.
Thank you, Marcel.
And present the work. And to everybody, let me thank you for participating. We already have a speaker lined up for August, the end of August, and you guys are going to hear all about it very soon. Everybody have a good afternoon or evening or morning, wherever you are, and we'll see each other soon. Thank you.
Thank you, Marcel.
Thank you, bye-bye.